Hello and welcome to the Great Climate Debate Podcast. My name is Jeffrey DeSena, and today I bring you our very first interview guest. Today I'm speaking with Brian Crow. Brian received his Master of Science in Atmospheric Science with an emphasis on climate science from Colorado State University in 2016. Shortly thereafter, he started work as a meteorologist at a Fort Collins-based meteorological statistics and precipitation analytics company, where he analyzes meteorological data to form predictive models of local precipitation. He was a founding member of CSU's 350.org chapter, and he wrote his thesis on quasi-periodic variation of eddy kinetic energy in the mid-latitudes of the southern hemisphere. If that didn't make any sense to you, don't worry, Brian explains his research in plain English in our conversation. If you enjoy the podcast today, please follow us on iTunes, Stitcher, CastBox, Podbean, SoundCloud, or YouTube. And please, share with your friends on whatever social media platform you prefer. Thank you for tuning in to the Great Climate Debate Podcast. Without further ado, I bring you Brian Crow. Hello and welcome. I am here with Brian Crow. Brian, thanks for coming on the podcast and being my first guinea pig.
Well, thanks for having me. It's a pleasure to be here.
Great. Well, it is really an honor to finally be able to get this thing off the ground. Our listeners will have a little bit of background on who you are, but if you'd like to give a little bit of introduction on what you do, how you've ended up here in Fort Collins.
Sure. So I actually have a meteorology and climate science background. I did a bachelor's in atmospheric science at University of Missouri, and that led me to come out to Colorado State to get a master's in climate science. But I've always been a little bit more of an applied weather guy. I'm just kind of interested more in day-to-day weather patterns and that sort of thing than I was, say, in larger scale climate science. So after I finished my master's, I ended up going back to work more in weather. And so now I do rainfall analyses for a small company here in Fort Collins.
Well, very cool. So what originally piqued your interest about meteorology? Was there some specific moment where you knew you wanted to go study the weather?
Yeah, I think there is for a lot of people in my field, but I don't know that I could point to one specific time. I think for me it was just sort of the collection of weather events that I experienced growing up. I grew up in St. Louis, Missouri area, so I saw everything from massive floods to, super intense thunderstorms to blizzards, all just growing up in the hills of Missouri. So I think I was just really intrigued by the variety and the intensity of different kinds of weather. And by the time I was in middle school, I was pretty sure that's what I was going to be doing with the rest of my life.
Well, very cool. Did you ever consider putting all this knowledge to use in maybe a different field? You've now kind of ended up, being a meteorologist. But were there any other options you had tossed around?
I was interested in astronomy and astrophysics as a young kid as well. So I guess I just always wanted to do something, kind of large scale with science. And physics. But yeah, I kind of toyed with that idea for a while, and then, even though meteorology is very math heavy, I think astrophysics would have been even more so, and doesn't have quite that tangibility and immediacy of the results that meteorology does. We're living in the atmosphere, we're not living in outer space. So, I think I just like having that tangibility to the science that I'm studying.
Oh, very nice. And so now you've definitely found a place where you're putting all that to very practical use. Can you describe a little bit about what you do with your company?
Yeah, so basically most of my work is producing rainfall analyses. So what'll happen is somebody who owns a dam, say, will come to us and say, hey, we have these safety standards we have to meet, and we have some hydrologic modelers who can help us analyze, what the worst case flood scenarios might be, that sort of thing. But they need rainfall statistics in order to run those hydrologic models. And so what I'll do is I'll go back through and make a list of the biggest, most impactful rainstorms from that area, in our period of record, so last 100, 150 years or so. And then I'll piece together the best analysis I have using some proprietary software that we have. And so, several storms later, we then have all these statistical techniques we can use to kind of maximize those and move them around and say, okay, what's the worst case flood scenario for this specific river basin? And so that's what we do. Basically provide dam owners and operators with rainfall statistics so that they can know what kind of floods to prepare for.
Okay, it sounds very useful, but I noticed that you were definitely referring to statistical models in your modeling. Is that just based on historical data, or are you also using physical models to validate that against?
Yeah, so the statistics part comes in by evaluating station data. So we pick stations with the longest possible period of record because they can give you the best possible idea of how frequently certain types of rain events occur. And so using, the collective of all the stations in an area, if you've got 100 stations with 100 years of record, well, that's 10,000 record years. Mm-hmm. So you can actually do a lot more with just a few long record stations than people realize. So yeah, we've only been keeping weather records for 100, 150 years, but a lot of times we can calculate with pretty good accuracy what the 1,000-year rainfall at a given place is. Mm-hmm. And a lot of that is that being able to trade time for space. So having, lots of long record stations in an area, you can start to back out some pretty extreme rainfall totals. And so it's just techniques that take advantage of all of the data out there rather than just relying on single stations.
Mm-hmm. Very interesting. So how would you go about validating those kinds of predictions? I mean, it's saying it's a once in 1,000-year rainstorm. I mean, we can't wait around for 1,000 years to see if that was right.
Right. So the best we can do really is try to fit observed events to the estimated probability curve. And so that's basically, we've got different statistical distributions that we can examine to see, how the characteristic precipitation frequency curve will fit that in a given area. And so, it really depends on the area and how much data you have to work with, but most times you can nail down your 10,000 to 100,000 year storm pretty well.
Okay. I won't dig too far into the weeds anymore on that before we lose all our listeners. But I would like to go back a little bit to your master's studies. Can you tell us a little bit about what you were studying and what you did your thesis in?
Yeah, so basically my master's thesis looked at some natural climate variability across both hemispheres, but mainly in the southern hemisphere. So I guess a little bit of background. You have the jet stream that runs around the high latitudes of the planet in both the northern and southern hemisphere. And the jet stream drives a lot of your storm activity. So, your low pressure systems that circle the globe, are in large part driven by the jet stream. And so basically the motion of the jet stream, where it's positioned, how wavy it is, all of that affects how much storm activity you have in the mid-latitudes where most people live. And so what we looked at was how frequently does the jet stream become more and less wavy? In other words, do you have these cycles of higher and lower storm activity? And as it turns out, if you look hemisphere-wide, you do. If you look at smaller scales, say like a quarter of the hemisphere, so even something that's like larger than North America, you don't really see this regular signal. But if you look at the whole hemisphere kind of pulses and fades with periods of storm activity on about a 25-day cycle. So that's basically what I looked at. And in part, we explore questions like that because, if you're trying to study climate change, you need to in part know what's going on there naturally anyway, so that you can kind of separate what's natural from unnatural. And so this is an example of a natural climate variation that we found that's embedded in the climate system.
Interesting. And were you working off of empirical data or models?
A little bit of both. So empirical data in the southern hemisphere actually kind of looks like a model because, as you can imagine, the southern hemisphere is 80% ocean, and the land masses that are down there are just generally not as populous as ones in the northern hemisphere. So you don't have a whole lot of first-order direct observations in the southern hemisphere. Instead, you have to rely on a lot of weather satellite data and then analysis models to kind of fill in the gaps. And so what I worked with was an interpolated data set called a reanalysis data set, where basically you take all the observations you have and fit them into, a very good high-resolution model, and that helps fill in the gaps for you. So in a sense, it was kind of both. I wasn't doing any modeling into the future or anything like that, but anymore there's almost no disentangling data from modeled information.
Interesting. And how far back did these data go?
So we had really high quality data back to 1979, so that's mainly what I worked with. Mm-hmm. Other data sets of that type can go back as far as 1850.
Okay, very nice. But you were looking at variations that were on like the month scale, so these were
Right.
plenty of time.
So 1979 to like 2015, which is what I worked with, was plenty of data to assess something that was going on like a monthly time scale. But obviously, the bigger the climate cycle you're looking at, the more and more data you need in order to suss that out.
All right, very interesting. And how did this fit into the larger research group? You were working as part of the climate dynamics group at Colorado State.
Yeah, so there are 4 professors in the climate dynamics group there, and they all look at different topics. A lot of them centered around the jet stream and its behavior. Some people have more of a climate change focus. Others are interested more in climate variability and natural climate cycles, that sort of thing. So it was just a variety of different topics. I don't know. I can probably help with more specific questions there, but it's a pretty broad topic actually that they research. So.
Okay, well, then let's dig into that. So maybe describe a little bit of who are some of these people. Maybe describe like who your advisor was and maybe what they were working on.
Yeah, so my advisor was Dave Thompson. He has looked at a lot of stuff in his life, but he's mainly known for his work with annular modes. The work I did was kind of an extension of this annular mode concept, but basically it's this idea that your flow around the hemisphere kind of expands and contracts over time, just in concert with a number of different forcings that help define the storm tracks in the atmosphere and that sort of thing. So he's done, a lot of his work is pretty technical, I'm realizing as I'm trying to explain it now. But yeah, he's well known in the field for really putting some interesting ideas out there in his PhD thesis, all related to how the storm track kind of grows and strengthens and weakens with time.
Mm-hmm. So I guess I'll ask another specific. Do you know anyone who's been working with that group who's not just looking at maybe natural variabilities, but possibly how other forcings like emissions or CO2 are actually changing those natural variations?
Yeah, so there's another professor in that group who is actually on my committee, is Libby Barnes, and she has been looking lately at how different amounts of warming affect the position of the jet stream across the North Atlantic, which has consequences for Europe and North America both. So if you think about, say your average jet stream position moves north by a couple of degrees, well, all of a sudden that might put places like Western Europe further south of the storm track than they would normally be, and that might leave them drier and warmer than they would otherwise be. So it's got consequences for places like Western Europe. In Eastern North America, we've seen some jet shifts already in the last 30, 40 years that might be causing all these nor'easters that it seems like we hear about every winter, where you can get just absolutely massive, crippling snowstorms up the East Coast. And so she's looking into what dynamics play into affecting those sorts of outcomes.
Very interesting. And how big is the group? Like, how many researchers are part of this?
I think when I was there, it was 4 professors and probably about 15 to 20 students. Most professors there have 2 or 3 masters, 2 or 3 PhDs, and maybe a research scientist or 2.
Yeah. And how much interaction did you have with each of these, your fellow researchers or the other professors, or were you pretty much just working with maybe your advisor and maybe a couple others?
Yeah, I'd say within my advisors group, I interacted with several people. There was a postdoc whose work kind of guided a lot of my master's thesis, so I worked with her a lot. And then I guess across the rest of the group, they tend to be the people that you see in classes all the time and that sort of thing. So I think there's a lot of camaraderie in groups like that, but I didn't directly collaborate with a lot of my fellow students on like papers or anything like that.
Okay.
And I think that was just the nature of, I was doing a project that was a little bit different. Other students will sometimes co-author papers together if their research has big areas of overlap, but I just happen to be doing something kind of different.
Okay. And for those who haven't really been part of academia, can you just describe your life a little bit as a grad student?
I mean, it was busy because you end up taking, especially during your master's, you end up both taking classes, which can be pretty intense. I mean, they make it a goal for classes not to take all your time because they want you to be doing your research. But, some of the homeworks and stuff get very difficult. Sometimes your homework is write this simple climate model, and so you end up coding up, something that's 200 or 300 lines completely from scratch, and you got to debug it and get everything working in order to, get that assignment done.
Yeah.
So some of the assignments and stuff end up pretty intense. But yeah, the main focus is your research, and so the whole time you're there, when you have a lower class load, it varies a little bit semester to semester. When you have a lower class load, you're spending more time digging into background literature on the topic your advisor has put forth for you. So you're reading a bunch of published articles and textbooks and stuff like that to try to get an idea of what do people already know about this question or this problem, and then you work with your advisor over time to kind of define what your interest is and what would be new and interesting research to do. And then you start picking away at it. And if you're an atmospheric science grad student, it means a lot of coding usually, because you work with huge data sets, just tens of gigabytes sometimes. And so the only way to process it all, you're not going to do it in an Excel spreadsheet. So you end up having to work in MATLAB or R or Python or a language like that to process these huge data sets and produce plots and that sort of thing.
Okay, maybe a bit of a weedsy question. Where do you get a lot of this data?
So I worked with the ECMWF reanalysis, and ECMWF is the European Center for Medium Range Weather Forecasting. They're better known for having the Euro model. So whenever you hear people talk about weather models, there's the American GFS model and there's the Euro. And so this is the center that produces the Euro. But they also run a version of the Euro that goes back and analyzes past observations. And so that's what I referred to before, the data set I was working with in the Southern Hemisphere.
Okay.
The Euro just analyzes the globe, I think 3-hourly time steps all the way back to 1979. I think they're working on extending it back even further. So we've got all this great data to work with, and that's an example of a reanalysis data set. Other people work directly with satellite data or radar data or just surface observations or whatever. So a lot of this stuff is available online. You just kind of have to know where to dig for it.
Yeah, okay. And was that kind of a draw for you to come to CSU to study that? Did you know that you were going to be doing a lot of coding, data analysis, or was it just kind of your interest, seeing that was what was open, and so you thought you'd continue into that, or was there a specific draw to this program?
CSU's Atmos program is really highly ranked, so that's what drew me to it. And then, coming out of undergrad, I was somebody who, had kind of had a realization in college that climate change was a much bigger problem than I had imagined it to be when I was younger. And so I was really interested in going somewhere to do climate science. And CSU has a very good reputation for that. As far as the coding and stuff like that, I had been warned I would have to code in grad school. It wasn't something I was looking forward to, but it's something you end up learning to do at least as well as you need to, once the time comes.
Okay, nice. And of course now we are moving into a bit more talk about climate change itself.
Yeah.
So I guess how did you get introduced to the idea, and when did you start thinking that it might be something that you'd want to research, know more about?
Yeah, so I can remember being fairly skeptical that we even had a climate issue, even as recently as graduating high school. But by the time I got into the atmospheric science program at Mizzou, where I did my undergrad, I met several other students there who were more interested in it than I was, and sort of over time, kind of showed me different resources, including different professors' blogs and different climate resources like NASA's climate page and that sort of thing. And so I started getting exposed to a lot more of this data that's out there and readily available to the public, but I just never found before and never looked into myself. And so I think just having influential friends who are well versed on the topic, and actually learning about thermodynamics and that sort of thing, in the course of my college classes, I just realized the extent of the problem and became a lot more concerned about the path we were heading down, collectively as a society. So that's why I wanted to do climate science for for grad school.
Yeah. So it sounds like there are certainly some people who enter the meteorology field not being, at least convinced of the science. Are there those of you who might have come in thinking that, well, it's actually really not a problem, and I want to learn that to prove that it's not? Did you ever have any of those classmates?
On occasion, but I think they were mostly in undergrad. And, meteorology and climate science are really different enough that you get people who, end up with meteorology degrees who, can forecast well, but maybe just don't grasp climate science and don't, aren't that interested in it or just outright skeptical of it. And that's actually kind of a big problem here in the US because, the leading science communicator for your average person is still your nightly TV weathercaster. And so many of them, either for, political and job concern reasons don't want to wade into that arena where, they're not actively saying on the nightly forecast, like, hey, notice how hot it's been lately, this is a little bit due to climate change. A lot of them aren't willing to go there, but then there's also a significant subset of them that just don't buy into it. Mm-hmm. And so it's interesting that, you can learn about thermodynamics and weather patterns and that sort of thing and still not be convinced of climate science because you really do need sort of those extra classes or exposure to those, other sources of knowledge than you would necessarily get just, on a path to be a TV forecaster or something.
Mm-hmm. And within the climate science community specifically, I'm sure there's not 100% consensus on exactly what we know, exactly what's going to happen. What kind of disagreements did you see within the community in terms of whether or not it's what we understand or just in terms of forecasting for the future?
Almost all the disagreement I saw was basically about details. I mean, there's plenty that's left to be discovered about climate change and understood better about it, but I don't think you really have any serious mainstream scientist who studies the topic that disagrees with the idea that increasing carbon dioxide in the atmosphere, is going to warm the planet. It just is. I mean, that's really simple thermodynamics that, they teach you in the second or third week of class in undergrad, So most of the disagreements I see are, well, to what extent does melting ice in the Arctic change the storm track for the mid-latitudes? Mm-hmm. And, how fast are we going to see glaciers melt? Mm-hmm. And, how much sea level rise can we actually deal with as opposed to, because there are some out there who would argue 2 or 3 feet of sea level rise is absolutely catastrophic because it's going to destroy half the coastal cities on Earth. And others are like, well, 2 or 3 feet we can build seawalls and we'll be okay. So really we got to be concerned about these higher end scenarios, mm-hmm. So most of the disagreement that I experienced within the climate science community was along those lines. Kind of, let's hash out the details because the larger framework is already really well understood and accepted.
All right, and just for your personal perspective, based on your experience, your research, what do you see coming down the pike, and what do you predict for our climatic future?
Well, so the UN IPCC reports, the Intergovernmental Panel on Climate Change, that have been coming out every 6 or 7 years, haven't really changed much over the last 2 or 3 publication cycles. The most recent one came out in 2013, 2014. And I think there's good reason for that. I think, these reports assess knowledge from literally thousands of papers across multiple fields, including geology, ecology, climate science, atmospheric science. And they kind of amalgamate all this information and then bring a huge number of scientists in together to weigh in on it. And so you end up with this very moderate, balanced viewpoint out of these reports. And so, honestly, I think those are great resources because they consider multiple different possible scenarios where they project, okay, what if, the whole world gets together and really decides to eliminate carbon emissions, in the next 10 years? What if we continue on the current trajectory? What if we burn even more fossil fuel than we already are? And so they've hashed out all these different scenarios. And, each of them is fairly realistic. And, when you look at the whole range of possibilities on the whole, I think they've probably realistically captured everything that they can. Mm-hmm. So I'm a big fan of those resources. I think they get a bad rep in the media for whatever reason. But really, so many thousands of scientists come together to work on them that there's no way any extreme viewpoints are getting through there, because you have the input of so many different people. It really tempers, everybody's projections, and you end up with a really, moderate report that, kind of speaks to what we do and don't know.
Yeah. And then from your reading of those reports and other resources, do you think that this is something that we really need to be concerned about, that we should be acting immediately or face serious consequences, or are you kind of in the camp of like, we'll just adapt as it comes?
Well, adaptation is going to have to be a component of it, because if we stop burning all sources of carbon emissions today, then by the time the climate comes into equilibrium a couple hundred years from now, we're still going to have 5 feet of sea level rise, and it's still going to be 1.5 degrees to 2 degrees hotter than it is today. So there's just a huge lag time in the climate system, because it takes forever for the massive oceans to absorb all that heat. So we're going to have to adapt. That's got to be a part of it. But I also think we should have started cutting carbon emissions 30 years ago, because, as I just mentioned, we've hit this point where, we can become carbon neutral tomorrow, and we're still going to have consequences to deal with for hundreds of years in the future. Not to mention there's already been serious strain on ecological systems all over the world, and in some places that are more sensitive to it than others, you could be looking at things like food chain collapse and agricultural collapse, and those are major, major consequences that we're going to have to do the best we can to avoid experiencing at all.
Yeah.
So yeah, I'm definitely in the very concerned and frustrated at the level of action we've seen.
Yeah.
Kind of camp.
So what's going through your head when you hear someone say, maybe on the nightly news, that like, well, we don't really know if climate change is even really happening, or we can't be sure that it's human activity and we can't do anything about it. So
anymore, I tend to tune a lot of those things out, in part because the people that they have coming on to say those things are generally the same people over and over, and they're people that are very motivated to say those things. So, I think what a lot of people don't realize is that the scientists that they get on, nighttime cable programs and stuff to come on and say that, climate change isn't a huge concern. Well, sure, they might be a scientist, but, more often than not, they're geologists who work, for the oil companies for 30 years or whatever, and now their retirement gig is being, an old respected PhD scientist, getting paid thousands of dollars to come on TV and say things that are convenient for, certain lobbying groups and that sort of thing. More often than not, you don't have climate scientists going on TV to discuss these things. And so, it's all about your sources, and, I just tend to pick my sources, pretty selectively. Like, I try to read very widely in terms of the actual science that's out there. But in terms of, climate information and mainstream media, I try not to pay too much attention, because there's a lot of bad information out there anyway.
Okay, good to know. But there are definitely a lot of people out there who, don't have a vested interest maybe in fossil fuels, who are still very skeptical of the science. Why do you think they might be so resistant to what we're hearing from the larger science community?
Well, I think mainly because it's inconvenient. Even if you're not somebody who has thousands and thousands of dollars or millions of dollars invested in an oil company, for example, a lot of people just don't like to hear that, you shouldn't be eating several pounds of red meat a week, and you got to stop driving your 12 mile per gallon giant lifted diesel truck, and all those sorts of things. People just don't like the consequences for them personally, is what it amounts to. And I think for so many people, it's a knee-jerk reaction to, well, if this is really as bad as the scientists say it is, then there's going to have to be a lot more government control of these things in order to prevent people from causing so much, carbon pollution and that sort of thing. And it's frustrating to me, because those are the conversations we should be having, is like, what should the role of private business versus the role of government be in addressing the problem? But it's frustrating because we seem to be caught in this cycle of just, is there a problem or isn't there a problem? That's the public discussion right now, when really that's been settled so long ago that it should be a total non-issue by now. Really what we should be discussing is, okay, so how do we do this without upsetting half the world, because we can come to solutions that don't involve, banning cars and banning red meat and, just big government and everything.
Yeah, well, we would hope so.
Right.
But speaking of changes, especially in lifestyle changes, is there anything that you've brought into your life to try to just reduce your own personal carbon footprint?
Yeah, I try to be mindful of it. Unfortunately, I'm not in a position right now where I can go buy my own house that has, a rooftop water collection system and solar panels and drive an electric car that I charge from my solar panels and all that sort of thing. But that's where I'd like to be in 10 years, For the time being, I drive a car that gets 40 miles per gallon. I ride my bike where I can. I don't eat nearly as much meat as I used to. I'm not totally vegetarian, but I've cut out a lot of it. So I just try to be conscious of it. The reality is it's a tiny drop in the bucket, and we really need top-down policy changes in order to really address the climate issue. But in the meantime, I don't want to do more damage than I have to. You know what I mean?
Okay, well, I think that's a good place to leave it off, and thanks for sharing those little tidbits about what you've done in your life, and those are also things that I've tried to do, and hopefully we can encourage others to jump on board. But you mentioned the IPCC reports. Are there any other resources you might recommend for people who might just want to know more?
There's a great website called Skeptical Science that does a great point-counterpoint where it'll show common points made by people who deny the problem of climate change, and then it'll link you to a bunch of different resources from scientific journals and that sort of thing that really show, well, this is what they say, but this is a misinterpretation of this science, or this is deliberately spinning this article, or that sort of thing. So that's a great resource for anybody who just isn't sure what to think about climate, because maybe you hear this certain point about, oh, well, climate's changed, thousands of years in the past, we should be going into an ice age, all that sort of thing. So they do a really good job of debunking all of those types of points on there. But just in general, there's several dozen, universities, government agencies that all independently publish their own temperature records and sea level records and that sort of thing. And it's really amazing to see how closely they all line up, even though they're all doing different things with different data sets. So that was one of the most convincing things for me, is seeing that, UC Berkeley's totally different algorithm, is super close to NASA's and is super close to, the United Kingdom's Hadley Center's analysis. So things like that just kind of really paint a consistent picture and can really help you understand what we've seen change so far and where we're headed.
Okay. Well, great. We'll try to get a hand on those and put them in the show notes so people can find out for themselves and do a little more reading. Well, Brian, thank you very much for spending some time with us. Glad that we could connect.
All right. Thanks for having me here.